Hey, Algebra students. In this lesson, we are going to be talking about displaying data in box and whisker plots. So we're back to another lesson on how we display data, like sort of a statistics lesson. It's not really talking about probability this time. We're just talking about displaying data in a way that is useful for us to look at it and understand what we're looking at. And that's what we're going to be doing in this lesson. A box and whisker plot is something you may have heard of before, but maybe not. It's not like a super common math topic, but it is really useful. And here's what it does. It displays your data by breaking it up into 4 different groups. First of all, it breaks it up so that you can see exactly where the median of your data is. Remember, median is one of the measures of center. It's not like the average where we divide all of the different data points by the total number of data points and get like a true center. The median is where you counted how many data points you had, and then you figured out how many of those, like what is the middle data point, and then you divided it. You said, okay, this is my median. Half of my data is below this point, half of my data is above this point. Then we find the median of the median below the median, and the median above the median. We'll take a look at what that means in just a moment if you don't understand. But we're going to find the first quartile and the third quartile, which split the data up even more into the first fourth of data, the second fourth, the third fourth of the data, and the final fourth of data. And then lastly, the last category is the minimum and maximum. If you're wondering what a box and whisker plot looks like, here's an example. So if we have a bunch of data on hockey goals per game, and I was collecting this data over several different games, I see that the median number of goals per game, like right in the middle, is 5. However, in a quarter of games, the players scored between 0 and 3 goals. Now, there was no game where 0 goals were scored. My minimum is 1. My maximum is 9. 75% of the data was 8 goals or fewer. Okay, those are the sorts of things I can conclude from a graph like this on hockey goals. Now, sometimes a question comes up whether your maximum and minimum amounts are what are known as outliers, values that are just so far outside of the range of most of your data that there has to be an explanation why they're so big or so small. Okay, we have a way of determining outliers. We use something called the interquartile range. It's the difference between the number that we call the third quartile and the number that we call the first quartile. And you take that difference and multiply it by 1 and 1/2. 1 and 1/2 times the interquartile range. Then you subtract that amount from the first quartile and see if you have a value that's less than that. Also, you add that amount to the third quartile and see if you have a number that's bigger than that. If you have a number that's less than the first quartile minus 1.5 times the interquartile range, that number is an outlier. Or if you have a number that's the third quartile plus 1.5 times the interquartile range, that number is a high outlier. Right now, I've been saying a lot of words here, and it's probably a little bit confusing, so we need to actually do some practice problems. We're going to find when working with quartiles, we have to do the exact same thing we did when working with median. We're going to have to take our data, put it in order, and find the middle. But this time, we're not just going to find the middle. We're going to find the middle of the bottom half, and the middle of the top half. Then we also need to find a minimum and maximum. All right, let's get started. In letter A, a trainer made a box and whisker plot of the number of seconds her clients could stand on a balance pod. Use the interquartile range to identify any outliers. Ooh, jumping right into interquartile range. Okay, well, this is actually a good one, though, because we've got some algebra to do with this one. So for letter A, what I'm going to do is take the first quartile. The first quartile is going to be this number right here. So 31, wherever the box actually starts. So I'm going to type that number 31. And then I'm going to look at the place where the box ends, that's the third quartile, that's going to be at about 51. Now I'm going to list 51 first. So we're going to do 51 minus 31. And then I need to take 1.5 times that amount. 1.5 times 51 minus 31. Well, 51 minus 31 is 20. 1.5 times 20 is 30. So 1.5 times our interquartile range is 30. What does that mean? Well, what we can do with that is add that number to the third quartile and see if we have a number that's beyond that. Our third quartile is 51, so I add 30 to 51 and I get 81. Because I don't have any numbers that are greater than 81. This number is actually less than 81 still. It's like 67. Because this number is less than 81, it is not an outlier. And this number is definitely not an outlier. I'm going to take like 31 and subtract 30 from it. That gives me 1. So as long as the number is greater than 1, it's not an outlier on this side. So I don't have any outliers. I don't have any numbers that are so far away from my first and third quartiles that we would say, hey, there's something really, really strange about that number and how big or how small it is. Because that's what an outlier is. It's a number that's really big or really small and doesn't seem to fit with the rest of the data for some reason. So in this one, we would say there are no outliers because everything falls within 1.5 times the interquartile range below the first quartile and above the third quartile. All right, let's move on to letter B. This is going to be one of those where we have to make a list of the data in order. All right, so here's my ordered list of the data. Now, I also notice that I have 1, 2, 3, 4, 5, 6, 7, 14, 15, 16 data points. What that means is I'm going to have to find the mean of my middle two to figure out what the median is, right? That's the center of my data. All right, so if 505.5 is my median, where is my first half of the data going to be? 2, okay? So my first quartile is going to be the median of the first half of my data. And when I'm considering the first half, I'm just considering these 8 values. That's going to be between these two. That's going to give me 475 plus 477 over 2 as my first quartile. My third quartile is the median of the second half of the data. But again, because I have an even number of data points here that I'm looking at, I need to find the middle by finding the mean of the middle two numbers. Okay, this is my first quartile. This is my median. This is my third quartile. I'm going to go ahead and plot these on a box plot. Oh, the other two things I need are my lowest data point, 387, and my highest data point, 605. All right, so you'll be making a box plot the best that you can on a piece of paper, putting a regular scale in the background, just like you see here. Because I'm doing this on a computer, I just made a box plot using a box plot generator in Algebra. But before I did this, I had to calculate the minimum, the lower quartile, median, upper quartile, and the maximum. And this is what our box plot looks like. All right, on to the next question. All right, back to making another Box-and-Whisker plot. A coach records the number of yards run by his players, and he made this list, and I just went ahead and made this ordered list and put them from least to greatest right away. I wonder if there's going to be any outliers in this list. 1 could be an outlier because it's really, really small, and 89 could be an outlier because that's a really large run. To figure out if there are any outliers, the first thing we're going to need to do is make a Box-and-Whisker plot. And to do that, we need to identify our median and quartiles. So our median, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 pieces of data. That's an even number, so my median is going to be between two numbers, 1, 2, 3, 4, 5, 6, 7, and 8. It's going to be between 23 and 27. Halfway between 23 and 27 is 25. That's my median. Now, for my first quartile, I'm just going to focus on the first half of the data. 1, 2, 3, 4, 5, 6, 7. Actually, it's kind of nice. In this set of data, there's just going to be one median right in the middle, number 19. 19 is the first quartile. And then the third quartile is going to be in the last 7 pieces of data. 1, 2, 3, 4. 37 is Q3. That means that my interquartile range is 37 minus 19, or 18. So I'm going to take my third quartile and subtract 18 from it. I get 1, and that is my lowest number. 1 is not an outlier. I'm going to take my third quartile and add 18, and that gives me, 45, 55. Anything above 55 is an outlier. That means that 89 is an outlier. It's a number that's so far away from the center that it's strange compared to the rest of the data, and there's probably an explanation for it. Maybe this is a runner who I got the ball and nobody expected that he had it, and he made it all the way from one end of the field to the other. Maybe he's just a really, really good runner compared to everybody else. But that's an outlier. All right, let's take a look at a box and whisker plot of this data. Looking at this data in its box plot form, it's pretty easy to see why that maximum is actually an outlier for this data. All right, and then for letters D and E, we're going to use this data on the populations of the 17 largest U.S. cities in 2005 in millions to see if there's any outliers. I've already put this one into a box and whisker plot, and I'll bet you can tell there's some outliers here. So what we need to do is figure out what 1.05 times the interquartile range is. Well, the first quartile is 0.7, and the third quartile is 1.75. If I subtract 0.7 from 1.75, I get 1.05. And then what I need to do is take 1.5 times 1.05. That gives me 1.575. So anything that's 1.575 plus the upper quartile of 1.75, let's just go ahead and add that in, plus 1.75. Any number greater than 3.325 is an outlier. Let's see if there's any numbers greater than 3.325 in our data. Well, I have 3.8 is an outlier. So whatever city had 3.8 million people, that's an outlier. And 8.1 is an outlier. Now, letter E says that I'm supposed to look at this without the outlier to see if the plot is better. So let's just delete our 2 outliers and see if our plot is a little more representative of what we would expect. Does this look like a better plot showing what the ranges of people living in cities is? Now, here's the thing. We got rid of 2 outliers, and maybe there's a way we can explain those outliers and why they're so big. One of those is probably like New York City, for instance. But now that we've removed them, we've actually changed the nature of our data set. Those were fair data points to include in the set. Even though they're big and they're outliers, it's not like they don't belong. So it is kind of interesting. Sometimes you do want to remove your outliers because there's an explanation for why they shouldn't be there. But sometimes your outliers should stay in your data because even though they skew the data, they belong in the data as a part of that data set. And I would say in this case, it doesn't really make sense. Yeah, it makes the display different, but it doesn't really make sense to remove them because they belong in the data set just like all of these other city populations belong in the data set. All right, that is how you work these box and whisker plot problems. You should do numbers 1 through 30 for next time.